So it makes sense that right after exponents, we would talk about logarithms. Okay, what is a logarithm? So a logarithm is the inverse of the exponential function, which is why we say it makes sense that we talk about it right after exponents. So what is a logarithm? It's the inverse of the exponential function. And we've talked about inverses before, right? So this should be familiar to you. The inverse is the reflection of the function in the line y equals x. Okay, so let's just sketch that. This is a very, very rough sketch of the exponential versus the logarithmic. So the exponential we're already familiar with. Here's our x and our y axis. And our exponential function, we know, gets very, very close to 0, and then it shoots up. Okay. The logarithmic is kind of the opposite. So here's the line y equals x. This is not going to look perfect. So the logarithmic function looks like this. Okay, and you can see that every point that we have on one side is a reflection of what's on the other side. Okay, and we can see that it's not perfect. I apologize for that. I just don't want to take the time to make it look better. It's not necessary here. Okay. Okay, so let's talk domain and range. So in the exponential function, we already know that the domain is all real numbers. So it goes from negative infinity to infinity. Okay, and you can see that here, that it's going to keep going to the left. It also keeps going to the right. It's going to take a long time when we get to the really high x values. The y's are going to be huge. Now the range, we also talked about this. Is anything greater than 0. It never reaches 0. And you could see it from the graph here. It never reaches the x-axis, but it gets really, really close. Okay. Okay, well, the logarithmic function is the inverse and it's a reflection in y equals x. So that means that our x becomes y and our y becomes x. And if that's true, then the range, which was originally our y values in the exponential function, now becomes our x values in the logarithmic function. So, and same thing with the domain. The domain that was in the exponential is now becoming the range in the logarithmic. So our domain, and we can see it on the graph, is any x value that's greater than 0. So it's exactly what the range was in the exponential. And you can see it here, that our x values do not go below 0 here. Okay, they approach 0, they never get to 0. And then our range is from negative infinity to infinity. And you could see that here, that our y values get lower and lower, and then they get higher and higher. Okay. Okay, so how does this work? Let's think about it mathematically. We're saying it's the inverse of the exponential. So let's actually take the inverse of the exponential function. So we start with the exponential. So we're going to say f of x equals b to the x. And we're going to find the inverse of this. And we already know that to find the inverse, we can flip the x and the y. But in order to flip the x and the y, we want to see really clearly that there's a y. So we're going to take that f of x and we're going to replace it with y. Okay. The second thing that we're going to do is we're going to do that flip. We're going to replace x with y and y with x. Okay, so now we have x equals b to the y. All we did was switch the x and the y here. And then finally, we need to solve for y. And we can't solve for y by doing like 1 to the y power, because if we did 1 to the y power over here, it would get rid of the y on this side, but then we would have x to the 1 over y. Okay, so this is where logarithms come in. We need to solve for y, and in order to do that, we need to use a log. So the way that it looks is y equals log base b of x. Okay, let's summarize what we just did here. First thing that we did was we replaced f of x with y. Second thing we did was switch x and y. And the last thing that we did was solve for y. These are the same steps that we used when we were finding inverses when looking at polynomial functions for the first time. Okay. Now let's look at this y equals log base b of x a little bit more closely. So again, I'm going to write down what this is. Y equals log base b of x. That's how we say it. Okay, what does it mean? It says b to the y power is equal to x. This is what it means. b to the y power is equal to x. Okay? If we identify this, the b is the base. Let me actually rewrite this down here. So this b is our base. This is for, this is our vocabulary so that we can easily refer to things. The b is the base, and the x that you see here, we call it the argument of the log. Okay, now we can actually convert back and forth between logarithmic and exponential expressions. And the thing to remember here is that the base of the logarithm is always going to be the same as the base of the exponential. So this is what it looks like in exponential form. This is what it looks like in logarithmic form. We're going to talk about this a lot more. The base here is the same as the base here, right? We have a b and we have a b. It's the same base. So the base of the exponential form is the same as the base of the logarithmic form. Okay. Another thing, and I will add this actually over here, and we'll add this a few times, but this is really important. Not what I wanted to do. Okay. I'm going to put it up here. This is the most important thing that you're going to hear. The purpose of a logarithm is to solve for an exponent. This is really important because when we get to in our next step, this is what's going to help you, knowing this. And you can see here that when we had to solve for y, when we had to solve for the exponent, what did we use? We used the logarithm. Okay, so the purpose of a logarithm is to solve for an exponent. Okay, what does this mean? This means that we could go back and forth between a logarithmic expression and an exponential expression. For example, if we have y equals log base 2 of 3, this is a logarithmic expression. Okay, and as we just said, a logarithmic expression is solved for the exponent, meaning the exponent is all by itself on one side of the equation. This is saying 2 to what power is equal to 3? The exponential form of this is exactly what I said. 2, the base of the exponent is the same as the base of the logarithmic. So here's the base of the logarithmic. So the base of the exponential is going to be 2. We know that a logarithm is always solved for the exponent. So the exponent is y. And then we have is equal to the argument. So this here is an exponential expression because it has an exponent. And the exponential expression is always solved for the argument. And I'm actually going to go back to the previous page. I don't know if this was 100% clear. This y is your exponent. So in every logarithmic expression, we have an exponent, we have a base, and we have an argument. Same thing is true for every exponential expression. Okay, so let's just do a bunch of going back and forth. Okay, we're just going to create a table where we have the exponential expression, and then we're going to have the equivalent logarithmic expression. Now, as I go through this, sometimes I'm going to start with the exponential. Sometimes I'm going to start with the logarithmic. What I would recommend is that you pause the video. If I give you a logarithmic, put it into exponential. If I give you an exponential, put it into logarithmic as practice. And then start the video again and just make sure that you did it correctly. Okay. So let's start with r to the w. Is equal to 5. So we're going to take this and we're going to put it in logarithmic form. So this is exponential form. This is logarithmic form. Okay. So we are given the exponential. We want it to look like this, meaning we want to solve for the exponent. So our exponent here is w. So this is going to be w equals. Then we have our log. We know that the base of the exponential is the same as the base of the logarithmic. So the base of the exponential here is r. That's going to be the base of the logarithmic. And then the argument is just 5. Okay, so the argument is like our answer in the exponential expression. Okay, let's do another one. Let's say that we have 6 is equal to log base 2 of x. Remember, that's how we say it. Log base 2 of x. I would also recommend that you practice saying. So we know the base of the exponential is equal to the base of the logarithmic. So the base of the logarithmic here is just 2. We know that a log solves for the exponent. So the exponent is 6. And the only thing left here is the x. So 2 to the 6 is equal to x. Okay, let's take another one. Let's say that we have 7 equals log base b of 3. So again, start with the base. The base of the logarithm is equal to the base of the exponent. So our base here is just b. The logarithm is solved for the exponent, so the exponent is 7. and this is equal to 3. Okay, next, 8 to the y is equal to 15. So the purpose of a log is to solve for the exponent. The exponent is y, so this is going to be y equals. We have our log. The base of the log is equal to the base of the exponent. Well, the base of the exponent is 8. And what's left over? 15. That's our argument. Let's do 4 squared is equal to 16. So this is an exponential form, okay? Notice in logarithmic form, this is 2 is equal to log base 4 of 16. The base is 4 in both. The exponent is 2. This is solved for the exponent, and then our argument is 16. 3 equals log base 3 of 27. So what is this saying? This is saying 3 to the third power is equal to 27. So it's just a different way of writing the same thing. One more. 2 to the 5th is equal to 32. So in logs, what this is saying is that the log base 2 of 32 is equal to 5. Okay? The log asks, what power do we raise the base to in order to get the argument? R to what power gives us 5? 2 to what power gives us x? B to what power gives us 3? 8 to what power gives us 15? 4 to what power gives us 16? 2. 3 to what power gives us 27? 3. 3 to the third is 27. 2 to what power is 32? 5. 2 to the 5th power is 32. Okay. Now a couple of quick notes. Just like when we talk about square roots, okay, we just write the radical sign, or when we're trying to say x to the first power, we don't write the first power. And the reason for that is that x to the first power is the most common, the first power is the most common power. So mathematicians can be kind of lazy and they don't want to constantly write something that they don't have to. So because of that, we say, well, we don't always have to write the base because there are some bases that are a lot more common than others, okay? In mathematics, one of the most common bases is base 10, okay? Everything in mathematics is based on 10, right? We multiply by 10, that just adds a 0. Why is this? Because we have 10 fingers. So way back when mathematics was first getting started, we used our fingers. We count on our fingers even when we're little kids. We start by counting on our fingers. So base 10 is one of the most common bases. So just to save a lot of time, we say if there is no base, then it's base 10. So just like if there is no power, it's power of 1. We're saying for logs, if there is no base, the base is 10. So log of x is the same thing as log base 10 of x. Okay, that's the same thing. We're just leaving out the base. So in fact, if you have base 10, you should not write it. Okay, you should not. It's not incorrect to write it. It's just not mathematically beautiful. So mathematicians are a little bit lazy, but they also like to be really elegant. Okay, just like in your solutions to a lot of your linear equations, I said just to be elegant about it, to be clear. We put x equals and then in braces, we put all of our solutions. This is the same type of thing. It's not elegant to put the base. So if you're dealing with base 10, you don't write the base. Now the thing is that there's another really common base, okay? But if we don't put the base for that other really common base, then we would be confused. So the other really common base is e. So if you remember when we talked about exponential functions, we said e to the x is the natural exponential function. This base is just as common because it turns out that in our world, particularly in the natural world, in nature, things increase at an exponential rate of e. So the number 10 is for us because we have 10 fingers and toes. But for natural growth, where we don't have any sort of man-made intervention, population growth without any sort of intervention from us, that's using the natural exponential function, just like with compounding continuously, right? But as I said, if we just wrote log x, how would we know whether it was base e or base 10? So to solve this problem, we use different letters. We just use ln. And that's log base e of x. So again, to be elegant, you would use, I'm just going to rewrite this x so that it's a little bit further away. Okay, log base e of x. And to be elegant, you would write ln, okay, and it's pronounced ln. That's how we would say it. Okay, and just like this is called the natural exponential function, this is called the natural logarithmic function. Okay, so this is what the logarithmic function is, but now we have properties of these logarithmic function. And exponents had lots and lots of properties. Logarithms only have 4. And we're going to state what they are. We'll prove a couple of them, not all of them. We'll prove a couple of them. And then in the next video, we'll talk, actually the next 2 videos, we'll talk about how we apply those. So there are 4 properties. We are going to be using these a lot, both in working with expressions and working with equations. So the first one says log base b of x times y is equal to log base b of x plus log base b of y. And this is called the product property. Not surprisingly, this is very much like exponents. In exponents, we said if you have the same base and you're multiplying, then you add the exponents. This is if you have one log and you're multiplying, you can split it into two logs and add. Okay, so very, very similar. You go from multiplication to addition. And the second property is very much like this. It's just that you go from division to subtraction. Sorry about that. So we're saying log base b of x over y is equal to log base b of x minus log base b of y. And this is called the quotient property. Okay, our next one. The next one says if you're taking the log of something that is being raised to a power, so log base b of x to the m power, this is the same thing as if you took the exponent and you moved it out to the front as a coefficient. So it becomes m times log base b of x. This is the power property. And the last one, which is actually doesn't even really have a name, it's intuitive, meaning you kind of would know it. So if log base b of x equals log base b of y, so you have the same base and the logs are equal to each other, then the arguments must be equal to each other. Okay, and we can say it the other way around too. If we know that arguments are equal to each other, then we know that the logs of those arguments are also equal to each other. So it works in both directions. Okay, so let's just do some quick proofs. We'll just prove two of them. Okay, we're going to prove the product property. The proof for the quotient property is pretty much exactly the same. It's just wherever you are going to see multiplication here, you would just use division instead. And wherever you see addition here, you would just use subtraction instead for the quotient property. So that's why I don't feel a need to prove both of them. So proof of the product property. And just before I do that, just some terminology, and I'll repeat this in the next video. Expanded form versus condensed form. So notice there's only one log on this side. That means that it's condensed. This is the condensed form. There are two logs on this side. That's the expanded form. So when we talk about applying properties, we're going to be talking about expanding logs and condensing logs. So in other words, starting over here and expanding it, or starting over on this side and condensing it. Okay. So proof of the product property. So product property says log base b of x plus log base b of y is equal to log base b of x times y. Okay, so we're going to prove it. So the first thing that we're going to do, and this is not so intuitive, so I'm going to walk you through it. But the first thing that we're going to do is we're going to do a little bit of replacement to help us. And we can do this, okay? We can replace whatever we want as long as we're not breaking any mathematical rules. So we're going to replace each of these logs on this side. And we're going to say, let's let m equal log base b of x. We need the statement let's, because the let tells people that we're doing this replacement. And if we let m equal log base b of x, then we could let n equal log base b of y. Okay? Again, we're totally allowed to do this. Now we're just going to put each of these in exponential form. So we're going to take the first one, put it in exponential form. The base of the exponent is the same as the base of the log, so it's b to the m power, because the log solves for the exponent, is equal to x. And if we do the other one, it's the same thing. B to the n power is equal to y. So all we did here was put the logs in exponential form. Okay, I'm going to continue up here. So the next thing that we're going to do is we're actually going to multiply x and y. So when we multiply x and y, we get x times y is equal to b to the m times b to the n. Why are we multiplying x times y? The reason why we would do it is we see it over here that we're doing x times y. So we want to kind of see what's happening. So there are a lot of times where in a proof, you look at what you have and you're saying, how can I get there? Well, I see an x times a y. Let me see what happens. And if it doesn't work out, I'll just go back. Okay, but here we would multiply x times y. And what that means is that x times y is equal to b to the m plus n. So how do we know this? We used the exponential property that, let me see how I wrote it. I want to use the same letters. We used the exponential property from a couple of lessons ago, that a to the x times a to the y is equal to a to the x plus y. That was the exponential property that we used. Okay. Okay, so now what we're going to do is we're going to take this and we're going to put it back in logarithmic form. So we solve in a logarithm, we solve for the exponent. The exponent is m plus n. Then we're taking the log. Base of the exponent is the same as the base of the exponential, so it's b. And then the argument is just x times y. So we just put it back in logarithmic form. And then the last thing that we're going to do is we're going to substitute back in. And this gives us our therefore. So therefore, log base b of x plus log base b of y is equal to log base b of x times y. And this is because we substituted back in for m and n. We proved it. We have the same proof here. Okay, we proved the product property. We're done. We did it. So we write our QED. Okay, and that's it. Let's do the proof of the power property. There are several ways to prove the power property. I'm just going to prove it in one way. But if you look it up online, you'll see that there's other ways that you could prove it. Okay, so the power property says if you have log base b of x to the m power is equal to m times log base b of x. Okay. So what we're going to do is we're actually going to use the definition of exponents in this one, because we have x to the m. So all we're going to do is we're going to expand this. That's how we're going to start. So log base b of x to the m, and here again we're trying to make the left side look like the right side. That's what we do in our proofs. This is equal to log base b, and x to the m is x times x times x, m times. So this is just definition of exponents here. That's what we did. We expanded. Okay. Well, but we know from the product property that we can split this into separate logs, right? We can use this to say, well, this is really just equal to log base b of x plus log base b of x plus log base b of x m times. And this is just using this product property of logarithms. Okay, well now we're actually done, because what we're saying is therefore log base b of x to the m is equal to, sorry, I wrote m. I meant log base b. Log base b of x to the m is equal to m times log base b of x. How do we know that? What's the definition of multiplication? We have m of these. If we had m2s, then it would be m times 2. If we had m y's, it would be m times y. Instead, we have m of log base b of x. So we just multiply. Definition of multiplication, when we add the same thing to itself multiple times, we can just multiply by how many ever times we're adding it to itself. And therefore, we have succeeded and proving the power property. Okay, and in the next video, we'll learn how to take logarithmic expressions and either go from condensed to expanded or to go from expanded to condensed. And that's it.